All right, so under our last topic of the fall semester, conservation of momentum. And what we have is I would like you to draw this if you haven't already. Maybe you're just reviewing this, but you can do this on 22, on the bottom half of 22. But draw this picture with the data. Pause the video at any time. I'm going to move through this quickly, but you're at home, so you can just pause it in order to draw. But the question I want you to ask is, write these down underneath, is did the runner score? What direction do they fall? So let's assume these guys come together and collide right before the goal line. And when they tackle each other, they kind of stick together, right? Because this guy's going to grab onto that guy. And what velocity do they fall at? And I think you can answer the first two right now. So try that on your own before I give you the answer. Does the runner score, and what direction do they fall? So does the runner score? The answer is no, because this guy has a momentum of 180, mass times velocity this way. And this guy has a momentum of, I'm going to call it negative. Well, let's just look at it like this. A velocity of 200, momentum. So this guy's got more momentum, so they're going to collide. They're going to fall to the left, and he's not going to score. But this is going to be your actual test question. What velocity do they fall at? But first, let's go through a few things. Okay, this is an advanced topic, and it's called a conservation of momentum, and it's actually just like the law of conservation of energy. Okay, instead of energy cannot be created or destroyed, it can only change form. Let's review that really quick. What that means is, you know, I have the bowling ball tied to the ceiling. If I start the bowling ball right here, I lift it up and I just let it drop. It's not going to go swinging off and hit the roof because it only started this high. It can't go higher than it started as because where'd that energy come from? Now if I push it, if I give it more energy, then it can go up beyond where it started at. But if all it has is its initial potential energy initial, then you're not going to end up at this potential energy final. Okay, energy must be conserved. And it's the same thing for momentum. This topic, this law right here, is now momentum. Cannot be created or destroyed. It can only change form. And the way that I write it is momentum total before collision equals momentum total after the collision. So let's watch a quick video to demonstrate this. But we know that however much our total momentum before is, that's how much our momentum after is. So we're almost ready for those guys. So in this video, this guy's in outer space. And you can't hear him, so I'll do the talking. Can I write on this picture? I cannot. Rats. He's talking about how, let's see if we can see this. First of all, this is pretty awesome. I love watching stuff in outer space. But watch this. Okay. Timeout video. Okay. This ball has a velocity of 0. And then he's going to give this ball a nice velocity here of whatever. When it bumps into this ball, this one's going to mostly stop, and this one's going to fly off. But we know that the velocity that this one flies off at, and the velocity this one kind of trickles to the side, it's going to equal to the original velocity because our momentums are conserved. All right. And let's see it in action now. see it again. So this one flies off with a little bit of velocity. Most of it's transferred to that one. But for the most part, momentum's conserved. And it's the same when they stick together. So it's got Velcro right here, and he wants them to stick together. This guy's got momentum, this guy has 0, and then they stick together. They'll fly off slower because technically the mass of the object increased. So the velocity drops and the momentum is conserved. And there they go slower. Okay, you get the idea. Cool space stuff. Back to our runners. Okay, let's answer this velocity question. I'm going to get rid of all this stuff. Okay, we need to start with this. Follow along with me. I know that, momentum before equals momentum after. So, what's my momentum before? Well, I've got mass times velocity of runner A plus mass times velocity of B. This guy is 180. This guy's going in the opposite direction, so I'm going to call it negative 200. So the momentum before is 20 in the negative direction, so it's 20 that way. So that means the momentum after is also 20 that way. So when these guys come together and hit, they're going to form a big mass and fall that way. So I know my momentum after equals 20, negative. What's my mass after? Well, if they stick together, it's going to be 80 plus 90. And that is 170. So now I can answer the question, what's my velocity after? Well, I've got P equals mv, 20 equals 170 times velocity, divided by 170. Velocity equals 0.11-ish meters per second. Okay, so we know step 1, we found the total momentum before. That tells us the total momentum after. Then we use the mass after to find velocity after. Let's do it when they don't stick together. This is called a elastic collision. And let's just do the same process. What's our momentum before? Well, it's mva plus mvb. Let's call it A and B. So that's 2 times 4 plus 1 times 0 is 0 equals 8 kilogram meters per second. So our momentum before equals 8 kilogram meters per second. So that means our momentum after also equals 8. And we need to find the velocity of this guy if we know this guy stopped and then this guy kept going. So it passed on this moving energy. So let's see, we have momentum after is the same as mva plus mvb. And we know that all of this stuff equals 8. Well, 2 times 0, this guy's gone, because it's 2 times 0. And now we've got 1 times velocity b equals 8, divide by 1, divide by 1. Velocity b equals 8. Okay, there's some practice problems called conservation of momentum on the inside the handout section of the momentum tab. Good luck on your test tomorrow.